Welcome to Lecture 3.4. In this lecture, I'll be talking about how we handle lone pairs when we deal with aromaticity. Now, lone pairs in resonance, let's just do a quick review of them. Carbon always has a negative charge with a lone pair. It's never happy to have one. And we can resonance stabilize it by moving that lone pair to form a pi bond, breaking this pi bond to form a lone pair on that carbon. If I number them 1, 2, and 3, we say that this is resonance stabilized. Right? The lone pair goes here now in this resonance form. And the idea, right, remember this is not an equilibrium, they don't go back and forth. The real molecule is a hybrid or a mixture of the resonance forms, and in this case, they're both equally stable. What that means, since both of these have the same lone pair on a carbon, is that that negative charge is going to be equally distributed between both carbons that hold that lone pair in the forms, right? So in this case, resonance greatly stabilizes that lone pair. When we look at heteroatoms, for example, like nitrogen, we can do a similar idea, right? The difference is that heteroatoms, like oxygen and nitrogen, are generally happy to have a lone pair. Now, this is still a conjugated system, and we can still generate resonance forms. That would look something like this. Right? This nitrogen would become positive, this carbon would become negative. Now, we can't draw such a nice hybrid like we did up above, because clearly the original resonance form is more stable and would dominate the overall hybrid. It's good to recognize, of course, that this double bond would have a bit of delta negative character, a trend that hopefully you're picking up is important in the beginning of this course, as we've covered it in, I think, both previous sections now. But importantly, the idea is that lone pairs can act in resonance, and we can see them in aromatic rings. So how do rings complicate things? The idea is that as they're drawn, atoms with lone pairs, like oxygen and nitrogen, and even a carbon with a negative charge, they look like they're sp3 hybridized, according to our typical rules. Right? However, the big distinction is that here, right, if the oxygen lone pair decides to do resonance, to enter the ring, so to speak, I like to say enter the aromaticity, or chooses to enter, what'll happen is that we'll have an aromatic ring. The lone pair can enter the pi system, right? If it does that, how many electrons will we have in that system? Well, we'll have 2 from this bond, 2 from this bond, and 2 from a lone pair. And by participating in that resonance, you would actually generate 6 electron pi system, right? This would then become somewhat sp2 in character. That's the principle, right? So this ring is absolutely aromatic. When you're looking at this ring, then, you may be very tempted to call it anti-aromatic, and this is a common mistake that many students make. The reasoning is that, well, this lone pair can absolutely make resonance forms that make sense, right? In theory, it could too enter the ring, enter that aromaticity. We would then have 4 total electrons in the system, right? 1 pi bond and the lone pair. However, if that's the case, why would we make a ring, right? Why would we, I mean, the ring is made, but why would the lone pair choose to go in? If going in is going to make a horrifically unstable anti-aromatic ring, what instead happens is that the lone pair, quote unquote, chooses to stay outside. It avoids participating in resonance, right? As I mentioned above, resonance generally happens to stabilize a molecule. While that lone pair could, in theory, enter, it leads to this horrible, diradical anti-aromatic ring that we discussed. And so instead what happens is this lone pair remains on the outside, right? Now it truly is sp3. If it's not going to be entering with resonance, now it's truly sp3. The consequence of that is that this ring isn't anti-aromatic. It's actually non-aromatic. And a big idea here is that anti-aromaticity, or being anti-aromatic, is virtually impossible with a lone pair. Let's take a look. If the lone pair enters the pi system, and we get the 4n plus 2 rule obeyed, it's going to become an aromatic ring, right? Examples of this we included above, but yeah, it's an aromatic ring. It's going to choose to stay, right? If the lone pair enters, it performs the resonance that it's able to perform and generates something more stable, it's not going to want to stop. It's not going to stay outside the ring. It's going to participate in that resonance, which is going to lead to the generation of an aromatic system. However, if it makes the 4n rule, that would lead to the generation of an anti-aromatic ring. So instead, it just leaves. And what we get instead is simply a non-aromatic ring. An example of this that's very commonly tested in biochemistry is looking at the aromaticity of our DNA bases. Now, for those of you that have done biochem, they typically skip over the detail of this, as it's a little advanced for biochemistry. However, we can understand it now, given our better understanding of how aromatic rings work. This is cytosine, which is one of the 4 DNA bases, or I guess 5 nucleic acid bases. Point is, we want this to be a very stable molecule. And indeed, it is actually an aromatic ring. To verify that, we can count the electrons in this pi system. We have 2 electrons here, 2 here. Now, this isn't providing electrons. This is a double bond that's outside of the ring, but there is a p orbital here, right? So far we have all the p orbitals lined up. The problem is, what do we do with this red one, right? If the red lone pair stays outside, if it chooses not to enter aromaticity, then this ring will be non-aromatic. Well, let's see what happens if it does. If it does enter the ring, we would have 2 extra electrons in the resonance, making a total of 6. 6 electrons fits the 4n plus 2 rule when n equals 1. So the lone pair actually chooses to enter. And what that means is a consequence, and what is typically the big key objective in biochemistry, is that that lone pair is not a basic site, right? Sometimes in biochemistry, we'll use the term H-bond acceptor, right? It's not able to accept an H-bond because that lone pair is busy. If that lone pair was to leave the ring and actually do something, it would break the aromaticity of the ring, which is very, very undesired. It's like cold moving towards hot. It's just not going to happen. So that is an unreactive lone pair. But many students get confused then because they see this blue lone pair and they think, well, what's going on there? Why is that one reactive? That's because that nitrogen is already participating in the aromatic system with its double bond, with its pi bond, right? So that lone pair is not needed. If it was to enter, that would be bad. So it is reactive. It's actually there. It can work as an H-bond acceptor. It's reactive. And that difference can really be best explained through the lens of aromaticity. With that in mind, that's all the theory we need for covering aromatic rings. Feel free to try some of the practice questions attached under this video to take a stab at understanding how rings can be aromatic, anti-aromatic, or non-aromatic. In the next section, we'll discuss reactions that you can do to aromatic rings. I'll see you there.